It is increasingly common for modern applications to run auxiliary tasks. For example, MySQL runs a deadlock detection task. Redis runs RDB checkpointing task to save the KV items. PostgreSQL has an auto vacuum feature to periodically remove dead rows. These tasks cover various categories such as fault detection, recovery, and resource management. Although the tasks are auxiliary, they are important for applications' reliability and performance in production. Auxiliary tasks share a few typical characteristics. They are regularly invoked and often long-running. In each invocation, the task reads the main program's latest state and performs inspection work. If it finds something interesting, the task will take some actions, and the task may also optionally modify the main program's state. Currently, most auxiliary tasks are running with the main program in the same address space, and that brings safety issues. A bug in the auxiliary task could result in the whole process to crash. A heavy task could also incur severe performance interference. Therefore, although the auxiliary tasks are designed for improving reliability and performance, they can paradoxically harm the application's reliability and performance. An alternative is to run the task in another process, for example, using fork. However, that limits the observability because the forked process cannot see the updated states. Furthermore, it cannot carry out modifications since they are in the different address spaces. Essentially, the current OS abstractions, process, and threads are not well suited for auxiliary execution because they force the developers to choose either high observability or strong isolation. The question is, can OS provide both properties that are desired for the auxiliary tasks? Providing sub-process isolation is not new. However, the existing solutions primarily focus on two scenarios. Solutions like SFI target extensibility, such as executing browser extensions. Other solutions like lightweight context focus on secure partition, such as executing key signing functions. But there's a third category that is underexplored, which is maintenance. Those tasks are trusted developer code. They are highly interactive and may also alter the main program state. To address this gap, we designed an OS abstraction called Orbit. Orbit provides several properties together. First, a buggy Orbit task will not affect the main program. An Orbit task can easily observe the latest states from the main program. Some tasks can alter the main programs and they can do safely. The Orbit task will not incur large overhead. And finally, Orbit task is a first-class schedulable entity. There are two challenges in designing Orbit. First, isolation and observability are contradictory because when something is isolated, it typically cannot see the updated information. Second, isolation is well known to be costly. Traditional fork is slow for modern applications that has large memory demands, and optimizations such as shared memory will break isolation. Our insights to address these challenges is that separate address space are still essential for isolation, but we can continually mirror the latest state to an orbit. To address the second challenge, we observe that the states inspected in each invocation are typically only a small portion of all the states. We provide Orbit as a set of APIs. Developers can easily create an Orbit, invoke the auxiliary tasks many times, and then alter the main program states. All of these are used directly in the same application code base, and can refer to any existing variables and functions. Here's an example of using orbit for MySQL delegate detector task. Developer can call the orbit create to first create an orbit for later invocation. This API requires a function that represents the entry of an auxiliary task. It looks similar to pthread creation, but with key differences. Orbit runs in a separate address space. It gets created once, but will not execute immediately. It can be invoked many times later. From the application point of view, the created orbits are bound to the main program. The orbit's initial address space is kept minimum, mostly only sharing code pages. Based on our insight mentioned earlier, the orbit's address space continuously mirrored fragments of main program's address space. The mirrored fragments contain all the variables that the orbit task will need to inspect. A problem is that the many variables used by the auxiliary task can have scattered creation time and creation location. Fine-grained mirroring would be very costly. We take a simple approach by coalescing them into a contiguous region we call orbit area. This requires the developer to first create an orbit area and then replace the necessary allocation point with orbit allocation APIs. But all the usage points do not require changes. To ease this process, we implemented a helper tool. For a given task entry function, the tool uses static analysis to find the list of allocation points that would be used by the function and its callers. Our paper describes this part in more detail. To invoke an orbit task, an explicit orbit call needs to be made. At each invocation, the kernel will make a snapshot on the specified states and ensure it is the state of right before the invocation. Then, the states are synchronized to the orbit side, and the entry function executes in the orbit side to inspect those states. We provide two APIs. The synchronous one will wait until the task has finished, while the asynchronous one will return right after we create a snapshot. Implementing an efficient and correct snapshotting mechanism is non-trivial. Simply doing data copy is slow and wasteful, and shadow memory technique provides weak isolation, and it also adds high instrumentation overhead. We choose to leverage the copy and write mechanism, and with our additional optimization, it provides good performance. We also take consistency and concurrency into our consideration. Let's start with the classic copy and write. All the active page table entries in the main program's orbit area are marked as read-only. As mentioned, the asynchronous orbit call can only return after the marking has done. This ensures that the snapshot is consistent, since any write after this point will trigger actual data copy. Then, we copy the PDEs to the orbit page table at the same address. In this way, the auxiliary task can execute the task transparently without address translation. One scenario to consider is multi-threaded applications. Since we could mark multiple PDEs, we need the marking to be done automatically for consistency. A simple approach is to pulse all the threads, but that is usually too costly. We observe that those multi-threaded applications often already have synchronization at the original call site. We thus rely on those application-level synchronization to ensure that the snapshotting area will not change. Another scenario is concurrent orbit calls. For example, when two lock wait happens, one deadlock detector could be running while the other just started snapshotting. To support this scenario, we serialize all the orbit calls and use a FIFO queue to store the information of the calls. In each invocation, we mark the PTEs and save it to a temporary PTE array and add it to the queue. Each time, the orbit will pop the earliest array and install the PTEs to its page table. But what if the main program modifies the state after we snapshot it? Would it affect the previous snapshots? The answer is no, because those writes will also trigger a page copy in the main program side and leave the snapshotted page in the queue unmodified. To further improve performance, we enforce several optimization techniques. Due to time limit, I will only talk about delegate object. For other techniques, please see our paper. We observe that some large struct may contain only very few useful fields. For example, this transaction struct is 900 bytes in size. Allocating in whole would waste orbit area memory and thus increase the snapshotting latency. Thus, we propose a delegate object which separates the allocation of those fields. The delegate object in this example is only 1/9 of the original size. Furthermore, for easier usage, we utilize the C++ reference technique to make a one-to-one binding of the corresponding fields. In this way, the original usage are transparent and need no code changes. Some auxiliary tasks need to alter the main program's state. One idea is transparently replace the modified pages. This sounds clean, but the page granularity can easily cause state merge conflict problem. Thus, we provide a more controlled alteration with Orbit Update API. It provides precise modification by copying fields byte-wise. If the orbit crashed in the middle, we also avoid partial updates. Here's an example. The orbit side will first create an update as a scratch space that will log and pack all the modifications carried out in the orbit side, but will not immediately apply to the main program. Then, we can add various types of updates. For example, adding raw data for custom use, adding precise field modification that records the field's memory address and its value. For some special operation that can't be done in orbit, we record its function pointer and arguments. Finally, orbit push will push back the updates in a batch. This helps prevent partial updates if the orbit crashed before this point. Later in the main program, it can pull an update and extract the custom data to check whether the victim is still alive or not. If it's finished before applying rollback, the main program can safely discard the modifications. We implemented Orbit in Linux kernel. We tested 8 tasks from 6 large systems, including 1 new task. We evaluated it in a virtual machine running Debian 10 with our custom kernel. We started with microbenchmark. We compare Orbit creates latency with fork. We show that with large memory footprint, Orbit is hundreds of times faster than fork due to the fact that the initial orbit address space is kept minimum. We then tested Orbit on real-world applications. The tasks come from various categories such as error detector, resource manager, and checkpointing tasks. To evaluate how well Orbit can provide isolation, we manually injected null pointer dereference in all the tasks and reproduced 4 real-world bugs. We also added 3 other bug types. For all the cases, Orbit successfully isolates the fault and does not make any impact to the main program. Let's see an example, the Apache proxy balancer. There was an infinite recursion bug that resulted in stack overflow and then segmentation fault. Thus, all clients connected to this worker will see a dropped connection. In the Orbit version, the isolated proxy balancer also isolates the seg fault. It prevents client's request from being interrupted. The main program can also safely restart the orbit task, and the client of the triggering request can now see a meaningful error message. We then tested how much overhead orbit would incur. We used the standard testing tools and stressed the workload to invoke the auxiliary task frequently. We showed that all the systems have acceptable overhead with a maximum of 10% and the median 3.3%. We also compared with fork. We implemented a simplified fork version that does not even make modifications back. We ran a bug case workload with 8 clients. The fork version shows 84% performance drop, while the orbit version only shows a slight drop. By throughput figures, orbit is 6 times faster than fork. Our optimization technique significantly helped. For example, the delegate object for MySQL transaction struct is about 1/9 of the original size, and the total size of the orbit area gets 96 size reduction. The page fault numbers per query is also reduced by 41%, and that helps improve latency. We see that the orbit call latency is 88% shorter, and the throughput increases by 91%. In conclusion, auxiliary tasks are increasingly common in modern software, but they can incur safety and performance issues. Existing OS abstraction do not address this trend well. We propose Orbit, an OS abstraction for executing such tasks. We show that Orbit provides high observability, strong isolation, and safe alteration, while also preserves efficiency and flexibility. Orbit is available on GitHub. Thank you. I'm ready to take questions.